All right, honors chemistry people, we are going to do some more chemistry today. So here we go, my messy desk with all my books. All right, so when we left off last time, we were talking about isotopes, and we're going to talk about some isotopes some more. We're going to do some more practice on calculating the average atomic mass, and then we're also going to do some practice of calculating mass number, proton number, electrons, and neutrons as well. Okay, so let's do this calculation of average mass. Here we go. So the element of boron exists in two isotopes. We have boron 10 and boron 11. One consists of 5 protons and 5 neutrons. The other has 6 neutrons. Proton number stays the same, or else it would no longer be an atom of boron. So remember, protons determine the element that we have. If we have a different number of protons, we have a different element. Okay, I can't stress that enough. So protons ID the element. Okay. The experimentally derived or determined masses of the two isotopes are 10.0129 and 11.0093 AMU. Remember, AMU stands for atomic mass units. Okay, so atomic mass units. From this data, calculate the average atomic mass of boron. Check your answer with the mass of boron on your periodic table. Note that the periodic table has the average atomic mass number of all the isotopes, not necessarily the mass of one particular atom of that element. Okay, so we've got boron 10, which is at 19%. So we're going to make this 19% a decimal. So that means that I'm going to make it 0.1961. So we're going to make that a decimal. And we're going to multiply it by the mass of the boron 10, which is 10.0129. And then we're going to make the boron 11 percentage also decimal, 0.8039. And we are going to multiply that by the boron 11 mass, which is 11.0093. Okay, so when we do that, let's pull out my trusty calculator. 0.1961 times 10.0129. So when I do that, I've got 4 sig figs here. So this is going to be 1.963, and I'm going to write that 5 really quickly, small, so that I know that it is not a sig fig. So let's do the other. 0.8039 times 11.0093. I've got 4 sig figs with this one as well. Looks like it 0.8039 times 11.0093. This will give me 8.8503. Okay, so I'm going to add those two up. So 5 plus 3 will give me 8. Let's take that off. Let's see, 5 plus 3 will give me 8. 0 plus 3 will give me 3. 5 plus 6 will give me 11. We're going to count that one. 9 plus 9 will give me 18. And then we're going to carry that one. 8 plus 2 will give me 10. Okay, now remember, I only had 4 sig figs here. Or to here, this, since we're adding, this is to the thousandth. So I need to round at the thousandth. That 8 tells me to round up. So 10.814 atomic mass units. So you know what? Let's check my thing. So if I look at boron on my periodic table, oh my gosh, this boron And this doesn't want to scroll for me. Boron, I have 10.811. Now remember, this last digit here is an estimate, okay? So it doesn't matter that I'm off on that because remember that is an estimate. So we got 10.814. So yeah, we're within our rights because that is an estimate. Okay, now let's go and talk about how we calculate protons, electrons, neutrons, all those things. So if I look at chlorine, my atomic number is 17. Now remember, the atomic number is also the number of protons. Okay? Remember, the mass number is the sum, I should write that as epsilon. Let's erase that. So the sum, we use the symbol epsilon for sum of protons plus neutrons. Okay, so protons plus neutrons is the mass number. So if I want to find the neutrons, can't I take the mass number and subtract the atomic number, which is also the proton number of 17? So 35 minus 17 will give me 18 neutrons. And you know, atoms have to have the same number of protons plus the number of protons has to equal the same number of electrons if it is an atom. Now, when we come to further on in the year, we will talk about ions. Ions don't necessarily have the same number of protons and electrons. They have what we call a charge, which means that the protons and the electrons are uneven. But up until now, we are going to talk about atoms, and they have the same number of protons and electrons. So our number of protons, 17, is also going to be our electrons. Okay, so there's a mass number. We have an isotope of chlorine 35. I want you to try it for 37 and zirconium and the other zirconium isotope. Give yourself a minute or so, stop this video, and then we'll check this, okay? So remember, here we go. Remember we said the number of protons IDs an element. So if it's chlorine, I'm going to show you this on my periodic table. If it is chlorine, we are going to look at chlorine right here. Let's see, I want to highlight this. Chlorine has 17 protons. So even though it's a different isotope, it's always going to have the same number of protons. So we're going to put 17 here because the number of protons does not change when we have a different isotope. The neutrons will change, but the protons will never change if it's the same element. Okay, so protons are always the atomic numbers. This is also going to be 17. Now the neutrons is what's going to change. Remember, finding neutrons, we can take the mass number minus the protons and get the neutron number. So 37 minus 17 gives us 20 neutrons. So those two extra neutrons is what gives it its bigger mass. Okay, so let's look at this next one, zirconium. So we have an atomic number of 40. Let's check it just to make sure on our periodic table. So if I check my periodic table, no, that didn't want to check my periodic table. If I check zirconium, zirconium's right here. I indeed have 40 protons. So let's go back to this. So I will have 40 protons. I have 50 neutrons. So, oops, I put that wrong. Did you guys see my mistake? I put that where the mass number should have been. Okay, so I do have 40 protons. Remember, neutrons plus protons equal our mass number. So 40 plus 50 will give us a mass number of 90. We will have the same number of electrons as we have protons. So we're going to have 40 electrons. Okay, let's look at this next thing of zirconium. Zirconium, once again, always has 40. It always is going to have 40 right here, 40 protons, regardless of what the isotope is. Okay, so we will have 40 protons, 40 protons. Okay, remember atomic number and proton number is always the same. Mass number is the protons plus the neutrons. So if I take the mass number minus the protons, I will get the neutrons right here. So 92 minus 40 will give me 52 neutrons. And protons and electrons are going to be the same as well, unless I have an ion. So that's going to be 40. All right? So that's pretty easy. So let's look at this. This is another way of writing notations here. So let me show you this way. So I could call this chlorine 35. This would be chlorine 37. This would be zirconium 90, and this would be zirconium 92. Notice I'm pulling these numbers from the mass numbers. So 37, this comes from the mass number. This is a different way of writing it. So on this top number, we have the mass number. And the bottom number, and a lot of times the bottom number is not given. This is the proton number or the atomic number. Okay, so those are two different ways that we use to write isotopes. So this would be, in the other way, this would be cesium-132. So those are two different ways of writing cesium. So the bottom number is the proton number. So I could say that this has 55 protons. I could also say that it has 55 electrons. Now to find the number of neutrons, I have to take the mass number minus the protons. So I'm going to take 132 and I'm going to subtract 55. And when I do that, I will get 77 neutrons. Okay, try B, C, and D. Just stop the video for a second and we'll check in just a minute. Okay, so I have cobalt 59. The other way that I could write this would be cobalt with a dash 59. Now, remember the bottom number is always the proton number. So this would give me 27 protons. It would also give me 27 electrons. Neutrons, mass number 59 minus 27, the atomic number, will give me the neutrons. So that will give me 32 neutrons. How'd you do on that? Okay, Tmethium. So we've got Tmethium 130 or 163. We've got 69 protons. We've got 69 electrons. 163 minus 69, that will give us 94 neutrons. Okay? Zinc 70. This is another way of writing zinc 70. We would have 30 protons, 30 electrons, and we will have 40 neutrons. Okay, how'd you do on that? All right, next thing, we're going to talk about the mole. Now, the mole is a super important concept. This is something that we use for the whole entire year. Okay, I really, really need you guys to get this because this is something we really use all the time. Okay, so I want you to realize that the mole is a counting number. We are just counting something like we do a lot. So if I go to the store and I want you to get me a pair of shoes, you're going to bring me two shoes, hopefully a right-footed shoe and a left-footed shoe. right? If you get me a pair of socks, you're going to get me 2 socks. You get me a pair of gloves, you're going to get me a pair of gloves. Hopefully a right-handed glove and a left-handed glove, right? So think about this. We will go and we will use counting numbers all the time. So let's change the color here. So counting numbers. Why won't this let me write? Think about this. If I have a dozen eggs and I ask you to go to the store and get me a dozen eggs, I'm going to be expecting 12 eggs, right? That's a dozen. Okay? A pair of gloves gives me 2 gloves. A pair of socks gives me 2 socks. When I buy paper, I get a ream of paper. And a ream of paper is 500 sheets of paper. Okay? When you go and get pencils, your packs usually are sold in the dozen. But guess what? Schools, we buy these huge packs. These huge packs are what we call a gross. How many of you guys have ever heard of that? A gross is a dozen dozens. So a dozen dozens. So that would give me 144 pencils. Okay, that's what a gross is. So when we do things with these counting numbers, we could still use dimensional analysis. Oh, and I can't spell. Come on. It won't switch over to the eraser. Dimensional analysis. Okay. So we're going to use dimensional analysis, just like we did with the metric system, but now we're going to use a mole instead. So here we go with the concept of a mole. Remember, it is a counting number, okay? As you will learn in a subsequent chapter, an individual atom is very small indeed. The mass of an atom is approximately 10 to the negative 24 grams, something that we really can't measure with our normal equipment, okay? Chemists have devised a system of relative atomic weights based on the element carbon as a standard. It turns out exactly 12 grams of pure carbon-12, remember it has to be the isotope carbon-12, is 6.0221367 times 10 to the 23 carbon atoms. We write this number out. It looks like this. We don't want to write out all those zeros. That's why we use the scientific notation, okay? We really usually round this out to 6.022 times 10 to the 23rd. We use those 4 sig figs. This number is called Avogadro's number. We call it Avogadro's number because guess what? He is the guy that came up with this concept. Now, his name was Amadeus Avogadro, Italian guy. He was brilliant scientist. This number would not be very convenient for measuring something like marbles, okay? A mole of ordinary sized marbles would cover the earth to the depth of about 6.5 miles, okay? However, it's very useful when we measure very small objects like atoms or molecules. For instance, a mole of water of molecules would occupy the volume of a little bit more than half an ounce, about a tablespoon. A mole of aluminum atoms would weigh just under an ounce. In fact, I've added a video to this where I've measured out a mole of certain things just to give you an idea of how useful a mole is. So be sure to watch that video. Okay? By the way, abbreviation for mole is MOL. You get to save the E, one whole letter. It's awesome. Okay, so the profundity. this is the big idea of today. It turns out that the atomic mass of the element in grams contains 6.022 times 10 to the 23, or 1 mole of individual atoms. So if I look at the periodic table and I look at the atomic mass, and I measure that out not in AMUs, but in grams, I will have 1 mole, or 6.022 times 10 to the 23 atoms of that element. Okay? The molecular mass of a compound in grams contains 6.022 times 10 to the 23, or 1 mole of those molecules. Okay? So here's the way we can use our unit or our dimensional analysis. Mass in grams, 1 mole with the molar mass divided by grams will go to moles. Or if I have a mole and I want to go to grams, 1 mole with grams on the top will get me to the mass. Or if I want to go from moles to atoms, if I have moles on the bottom and Avogadro's number on top, that will get me atoms. But if I have atoms or molecules and I want to get to moles, if I divide by Avogadro's number and put moles on top, I can get to moles. So this is how I get back and forth between everything. And moles are the middle way. They're in the middle of this. So I can go from atoms to moles to mass, or mass to moles to atoms, back and forth. And it's a really easy way to count. So let's do some examples here. For example, the atomic mass of aluminum is 26.98 AMU. So let's look at aluminum. Let's go to the periodic table. So if I look at aluminum, and I want to check out aluminum right here. Aluminum is right here. Whoa, why did that do that? Wow. So aluminum, 26.98 grams right there at the bottom. Okay. So I have 26.98 AMU. So if I get 26.98 grams of aluminum, I would have exactly 6.022 times 10 to the 23 aluminum atoms, or 1 mole of aluminum. Notice I have 4 sig figs here, so that means I need 4 sig figs here. So let's look at this. How many grams of copper do I need to have 1 mole of copper? So let's use our unit analysis. I'm going to start out with what I have. I have 1 mole of copper. And I'm going to look at the periodic table to look and see what copper's mass is. So if I look at copper, I've got 63.55. Now remember, we are going to round when we do things to the periodic table. We are going to round to the nearest hundredth of a gram when we do this. So 63.55 grams will give me 1 mole of copper. So I'm going to look at this, and I'm going to put 65. So 1 mole of copper gives me 63.55 grams of copper. My moles of copper cancel. 1 times 63.55, I've got 4 sig figs here and 4 sig figs there. 63.55 grams of copper. Okay. Now what if I wanted to do 2 moles? Could I do the same thing? Yeah. I'm still going to use the same conversion from the molar mass on the periodic table, but I'm going to start off with the 2 moles of copper. Now I want my moles to cancel, so I'm going to put 1 mole on the bottom. And when we looked at the periodic table, we said that 1 mole was 63.55 grams of copper. Now remember, we got that from the periodic table. Let's look at that again. $63.55 grams. Okay, remember we're rounding at the hundredth. Okay, so my moles of copper cancel. 2 times 63.55. Remember, we have 4 sig figs. So when we do that, let's do the 2 times 63.55. We will get 127.1 gram of copper. Okay. How many grams of copper are needed to have 0.75 moles? We're still going to use that same conversion. So I'm going to start with the number that I know, 0.75 moles of copper. I want my moles to cancel, so I'm going to put it in the bottom. 1 mole of copper is 63.55 grams of copper. Now remember, we're getting that relationship once again from the periodic table. Okay, my moles of copper cancel. And I'm going to take 0.75 and I'm going to multiply it by 63.55. Remember here, I only have 2 sig figs. So we're going to round to 2 sig figs. So let's do that. Our calculator spits out this, 47.6625. That 6 tells us to round up. So we're going to report this as 48 grams of copper. Okay. Now, can I do it the other way? Can I start with grams and get it into moles? Oh yeah, I can use this conversion that we've been using and I can flip it. So let's start with the number that I was given here. I've been given 35.6 grams of copper. Now I don't want grams, I want moles. So I want my grams to cancel. So I'm going to put the 63.55 grams on the bottom. And I'm going to put moles on the top. So 63.55 grams of copper will give me 1 mole of copper. Notice my grams of copper cancel, and I have moles of copper, which is what I want. Okay, so now we're going to take 35.6 and we're going to divide it by 63.55. So 35.6 divided by 63.55. Now, our calculator spits out this crazy amount of numbers, 0.56101888 and blah, 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 like so much. We have 3 sig figs, so 1, 2, 3. So we're going to report this as 0.561. And our units now are moles of copper, 0.561 moles of copper. Okay. How many moles of copper are present in 4.5 times 10 to the 5th kilograms? Now, our relationship here is in grams, so we need to get our kilograms turned into grams. So that's the first thing we're going to work on. 4.5 times 10 to the 5th kilograms of copper. Now, 1 kilogram, if you remember, is 1,000 grams. So my kilograms cancel, and I now have grams. I can now still use this relationship that we've been using with the grams on the bottom to cancel out the grams. 63.55 grams of copper will give me 1 mole of copper. Now remember, once again, we got that relationship from the periodic table. Okay, my grams cancel out, and I'm left with moles. I've only got 2 sig figs here, so I'm only going to be able to report 2 sig figs. So when we take 4.5 times 10 to the 5th, multiply it by 1,000, divided by 63.55, we will get 7.1 times 10 to the 6th moles of copper. Okay? How many atoms are present in that? So can we go from moles to atoms? Yeah, we can. We can do that using Avogadro's number. So I'm going to start from the beginning. 4.5 times 10 to the 5th kilogram of copper. The first thing we want to do is get out of kilograms. So 1 kilogram of copper will give me 1,000 grams of copper. And then the next step, we're still going to use this. I want my grams to cancel. 63.55 grams of copper will give me 1 mole of copper. So my kilograms cancel, my grams cancel. I have moles, but I don't want moles. I want atoms. So to get from moles to atoms, I'm going to use Avogadro's number. I want moles to cancel, so I'm going to put moles on the bottom. 1 mole of copper will give me 6.022 times 10 to the 23rd atoms of copper. Okay, so my moles cancel. I now have atoms of copper, which is what I want. So we're going to take 4.5 times 10 to the 5th multiplied by 1,000 divided by 63.55 multiplied by Avogadro's number here. Notice I have 2 sig figs here. So when I multiply this all out, I will get 4.3. Why won't this let me write? 4.3 times 10 to the 30. My computer is thinking. 4.3 times 10 to the 30 atoms of copper. Okay, so that's quite a lot. I can take kilograms, thousands of kilograms of copper and still count how many atoms I have. Okay, just a little bit more. To find the molecular mass of a compound, we simply add the individual atomic masses of each element in that compound. For instance, water has 2 hydrogen atoms and 1 oxygen atom in the compound. The molecular mass would be the mass of 2 hydrogen atoms and the mass of 1 oxygen atom. So we're going to round each one to the 100th. Okay, so if I take hydrogen, let's look at hydrogen here really quick. And I look at what hydrogen is. I've got 1.0079. So that's going to round to 1.01. Okay. And if I look at oxygen, oxygen is 16.00. So 15.999 is going to round to 16.00. So those are the numbers that I'm going to use for water. Okay, so 2 right here, 2 for the 2 hydrogens times the 1.01, and just 1 for the 16 for the oxygen. When we add that together, we get a mass of 18.02 atomic mass units. So if I do that in grams, that will give me a mole. So if I have 18.02 grams of water, there will be 6.022 times 10 to the 23 water molecules, or 1 mole of water. So how many grams would I need for 2 moles of water? So we're going to use this relationship right here to figure that out. So 2 moles of water. I don't want moles, do I? So if I put moles, right? 1 mole of water gives me 18.02 grams of water. Okay, so my moles of water cancel. 2 times 18.02, notice I have 4 sig figs here, will give me 36.04 grams of water. So a little over an ounce. Okay, we're going to leave it at that. We're going to do a lot of going back and forth between molecules and grams, atoms and grams, avocados number and grams, avocados number and moles, and vice versa in our homework today. All right, hopefully this helped. We'll see you later. Bye.